Assalamualaikum. My name is NOUFAH and meet my amazing teammate which is AZRA and IZZAH. Today, we will be presenting two topics under the application of differentiation. The first one are related rates where we will be focusing on rate of change, and the second one is applied maximum and minimum problems. So, what is differentiation actually? Differentiation is a method of finding the derivative or the rate of change of a function. So, there are a few applications of differentiation such as related rates, determine increasing and decreasing functions, relative maxima and minima, applied maximum and minimum problems, mean value theorem, and lastly Rolle's theorem. But don't worry guys, me and my friends will be guiding you through the subtopic that we'll be presenting today.
Before we get to the questions, let's know first about it. The related rates in differential calculus related rates involve two or more variables that change at the same time, possibly at different rate. The rate of change is usually with respect to time.
Now let us go to the objective of the question in the related rate problem. The idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. The procedure is to find an equation that relates the two quantities, and they use the change rule method or implicit differentiation method.
So the problem statement is a cylindrical water tank is being filled at a rate of 10 cubic meters per minute. If the tank has a radius of 5 meters, how fast is the water level rising when the water is 3 meters deep? The keywords for this question is 10 cubic meters per minute and radius of 5 meters. So what are we going to do with that? For this solution, we will use the chain rule method to solve this problem. Okay, let's move to the first step to solve this problem. The first one is we need to know and write the formula for volume of cylinder. So what is the formula for volume of cylinder? The formula is V equal to pi r squared times h. R is for radius and h is for height. The second step is we need to identify two things, which is the given information and the unknown information. For the given information, the first one, the question mentioned 10 cubic meters per minute. That means we will write it dv over dt equal to 10 cubic meters per minute. Why is it in positive value? It is because there's another keyword in the question, which is be filled. Filled something that doesn't have anything until it fills with sort of medium could be interpreted as positive value for this question. Let's move to the unknown information. The rate at which the water level height is rising, so we will write it as dh over dt to represent this unknown rate. So the equation will be expressed like this, where dv over dt was known 10 cubic meters per minute, pi and r were given constant, which is the formula of cylinder, and dh over dt was our unknown. We don't know the answer yet, so we just put the pi and r and the radius equal to 5 meters. But how do we apply chain rule to this unknown information? Here's how. First, we treat pi r2 as a constant since the radius doesn't change. Second, we differentiate v with respect to t on the left side. Third, on the right side, we differentiate h with respect to t, keeping pi r2 as a coefficient. This gives us this equation. This is a direct application of chain rule, where we are differentiating a composite function v as a function of h, which is a function of t.
After we have successfully identified what type of formula to use for the cylinder, we need to differentiate the formula using the change rule as shown in the slide, which is dv over dt equal to pi r squared times dh over dt. After the differentiation is complete, we need to assign the value of the radius and height into the formula. Fifth step is to assign the value for the rate, so we assign 10 equal to pi r squared times dh over dt. Then we will get 10 equal to 25 times dh over dt, or 10 equal to 78.54 times dh over dt. Lastly, we solve dH over dt, where we make the dH over dt as a subject matter by swapping the position in the equation of tan equal to 78.45 times dH over dt. It will be dH over dt equal to tan divided by 78.54. We will get the answer is 0.1273 meters per minute. Therefore, when the water is 3 meters deep, the water level is rising at approximately 0.1273 meters per minute.
The conclusion for the related rates are, if we know how the variables are related and how fast one of them is changing, then we can figure out how fast the other one is changing too. So now let's move on the applied maximum and minimum problems.
For applied maximum and minimum problems, you might be wondering, what is applied minimum and maximum problems, right? Well, it is the process of finding maximum or minimum values, which is called optimization. Many application problems in calculus involve functions to find maximum or minimum values in real life. Applied maximum and minimum problems are usually used to maximize the profit of a company or to minimize the cost of creating a particular object. However, in calculus, it is to calculate the highest and the lowest point of a curve in a graph or to determine its turning point. And last but not least, is to be able to solve the question by using suitable and correct formula. A manufacturing company is designing a new open-top storage container. The container needs to be hold exactly 120 liters of liquid. The design specification required the length of the container be exactly 3 times its width. The height of the container is variable. The first question is, prove that the total surface area A of the container in square meter can be expressed as a equal 3W square plus 0.2W, where W is the weight in the meters. Next question are, determine the optimal dimension, length, width and height of the container that will minimize the amount of material used in construction.
So let's begin by defining our variables. We will use W for the width of container, L for its length and H for its height, all measured in meters. The volume of the container will be denoted as V in cubic meters. Now let's consider the information that are given. We know that the length is exactly 3 times the width, so we can write L equals to 3W. We are also told that the container must hold 120 liters, which is equivalent to 0.12 cubic meters. Recall that the volume of rectangular is given by V equals to L times W times H. Using this information, we can express the height in terms of the weight. We start with the volume equation, which is 0.12 equals to 3W times W times H. Simplifying this equation, we should get 0.12 equals to 3W squared times H. And next, we have to solve for H. We find that H must be equals to 0.04 divided by W squared. Now let's calculate the surface area. For an open-top rectangular container, the surface area is the sum of the areas of the bottom and 4 sides. We can express this as A equals to LW plus 2LH plus 2WH. And then we substitute our known values. We should get A equals to 3W squared plus 2 in bracket 3W, another bracket 0.04 divided by W squared plus 2W in bracket 0.04 divided by W squared. This should simplify. A equals to 3W squared plus 0.24 divided by W plus 0.08 divided by W, that further reduced to A equals to 3W squared plus 0.32 divided by W. Thus, we have proved that the surface area can indeed be expressed as A equals to 3W square plus 0.3W divided by W. So for the question 2 Roman, determine the optimal dimension to minimize the material used. To find the optimal dimension, we need to minimize the surface area function we just derived. So we will start by finding the critical point of this function. To do this, we take the derivative of A with respect to W and set it equal to 0. So the derivative is dA over dW equals to 6W minus 0.32 divided by W square, and setting this to 0 should give us the equation 6W minus 0.32 divided by W square equals to 0. Now, we need to solve this question for W. So we have to multiply both sides by W square, and we get 6W cubed equals to 0.32. And then we have to divide by both sides by 6, and we should find that W cube is equals to 0.053333, and taking the cube root for both sides, we should determine that W is approximately about 0.3778 meters. With the width determined, we can calculate the other dimension. The length being 3 times the width is approximately 1.1334 meters. The height which we earlier expressed as 0.04 divided by W square comes up to about 0.2803 meters. To confirm that this critical point is indeed a minimum, we can check the second derivative of our surface function. The second derivative is positive for all positive values of W, confirming that we have found a minimum. Therefore, we can conclude that the optimal dimensions for the container are approximately 0.3778 meters in width, 1.1334 meters in length, and 0.2803 meters in height. This dimension will result in the minimum surface area, thus minimizing the amount of material needed for the construction while satisfying all the given conditions.
Therefore, the conclusion for apply maximum and minimum problem is identifying the right formula and encompassing both first and second derivative currently will lead to a solid answer for a maximum or a minimum cost. I think that's all from us. Thank you and Assalamualaikum.